All right. Good afternoon, everyone. So today I will talk about diagnostic methods I worked on for my PhD research involving diagnostic studies on measuring the airborne sound transmission through building partitions. Okay, a brief overview. We'll look at what my problem was and what sort of my motivations of the study were, and then we'll talk about the transfer path analysis methods that I sort of applied to my study, and look at their applications and some of the methods and some case studies. Okay, so the sound insulation of a partition, as we know, is typically measured in a transmission suite between two reverberant chambers using well-established standard methods. And so typically we get some sound reduction index results in third octave bands. And what it tells us is basically how much portion of the incident energy was transmitted. So we know now how much of that energy was transmitted by the complete partition, but we don't know how the sound is transferred through the partition, like maybe through various paths of the partition. And if there are weak paths in the partition, which are, taking down the overall sound insulation of your partition. Okay, so those motivations. So nowadays, what we have is typically in build constructions, we have very complex multi-layered systems to offer superior sound insulation, which have different kinds of elements. You can have studs, you have ribs, you have cavity absorption, you have different kinds of constructions. And in that case, the sound transfer or the sound contributed by these elements will be different depending on whatever scenario you have. And so it then becomes quite important if you are trying to diagnose a noise issue or something to find out if there are really any weak links in your partition which are adversely affecting the performance of your partition. So depending on that, I had some aids of the study whereby I had to characterize the airborne excitation on the partitions, then diagnose the sound transfer and measure the contributions, source and path contributions to the receiver pressure. And then in the end, combine testing of the sound reduction index with the contributions to have like a complete test where you measure SRI and the diagnostic contributions as well. Okay, so to tackle this problem, I first sort of took the approach from transfer path analysis, which is a well-developed method in vehicle acoustics, where you have the diagnosis of a structure-borne source in the vehicles, where you have different structure-borne sources like the engine, you have the tires, and you have the chassis and the wheels. So you have to diagnose the contributions of each of those individual structure-borne sources in order to get the desired sort of like acoustic performance inside your vehicle. So our problem is sort of the same. So using the in-situ TPM method, which is based on block forces, you can characterize the source in situ. So that would be helpful in this study as well. So quick introduction, what we do in TPA is we have a system which can be very simply modeled as a source receiver system. So in any sort of dynamic system, source, which is the active element of your system, provide the energy to the system, and say subsystem, which is called the receiver, which will vibrate, or if you have a cavity, it will have a pressure response due to the action of your source. And the common boundary between the source and receiver is the interface where the source is acting on. So now we apply that same thing to our problem here, where you have a partition between a source and receiver room. Okay, and so our problem is then to characterize and measure the airborne sound transfer. So as we saw, using TPA, we can model that system as a source receiver system. So two challenges here. Sorry. So typically in TPA, we have a structure-borne source. But here we have an airborne source. And what happens, because we have an airborne source, we have a continuous excitation on the surface. So we can't really pinpoint, okay, there's the basically points of connection, or there's the discrete interface between the source and receiver. So what we essentially get is a continuous interface all over here, because the excitation is acting all over the partition. So in that case, what we can do is to avoid the challenges in just using a continuous excitation or a continuous interface. We can discretize this interface into discrete areas. So what we have now is sort of like sampling the interface, basically. It's like sample signals, sampling the interface, but in the spatial domain. Okay, so we get all these discrete interfaces. And if we have a discrete interface, then on each discrete interface, now we can diagnose the pressure by the block forces. And once we have diagnosed the block forces, then we can predict the receiver response by using the measured vibroacoustic transfer functions and the measured block pressures. Okay, forces, sorry. All right, so how the actual methodology looks like is, so first we measure the frequency response functions and the operational measurements. So using the impact testing with the hammer, we first measure the accelerances at discrete locations all over the panel, and then we simultaneously we also measure the vibroacoustic transfer function, which is here inside your receiver volume, with respect to the force at different discrete interface locations. And then in the operational measurement, you have a, let's say, a loudspeaker which will simulate a excitation, and you measure the operational accelerations and pressures. And when you have that, then you can measure the block forces using that inverse problem, basically, where you have measured the accelerances and operational measurements, and you find the block pressures. So what these block pressures do is they characterize one excitation by forces. So what you have here is basically you have some pressure excitation, and you get an equivalent system where you have modeled that excitation as a equivalent point forces at different discrete paths. Okay, so you can quickly validate this technique, predicting the receiver side response. Okay, and here what we do is we assume that if our sound transfer is just taking place through the partition completely and any flanking is negligible, then you can predict the sound transfer using the TPA approach, that's the in-situ prediction, and compare it with the measured pressure. And if they are similar, then we can say that the method is validated. So I used that for, I did the validation for a few case studies. The results I will present later. But once you have validated it, then you can go on and actually measure the contribution. So to measure the diagnostic contribution, so starting with just what the people do in TPA is measure the source contributions, where they diagnose the sources. They will diagnose the block forces and then measure its contribution, okay, using the block force and the individual vibroacoustic transfer function. But in our study, for diagnosing the sound transfer through partitions, we are more interested in finding the path contributions rather than the source contribution. So when you have a source contribution, it diagnoses the contribution of the force, and the radiation is through all the partitions. If you have a force there, your whole partition is radiating, okay? But what we want to diagnose is we can have whatever excitation up there, but we just want to look at what's being radiated, or what's the contribution of just, let's say, one path over there. So that's sort of the main problem. We can also do that, the same data, by characterizing the path as a, let's say, like a simple volume velocity radiator, okay? And you can relate that to the receiver side pressure by the acoustic transfer function between that volume velocity radiator and the pressure there. And to measure the acoustic transfer function from there to there, you can do that by just measuring the vibroacoustic transfer function and the structural FRFs that we measured. So this sort of formulation is a novel formulation where if you have to measure the acoustic transfer function where you can't apply a direct or reciprocal method, you can use this formulation to measure, okay? So we can find then the source and path contributions, but both of these approaches are inverse approaches, because the block forces are measured inversely And here as well, if you see, the acoustic transfer function is measured through it by doing an inverse here. So what we want is, we want something quicker, because if we are doing an inverse approach, we have to measure the whole structure and so on. So ASCA, which is the inverse airborne source contribution analysis, is purely experimental. We have really long measurement times. We need a large number of velocity and pressure sensors. If you imagine a whole partition being tested, you need so many sensors. Because it's an inverse process, you have the calculation is very prone to inversion errors. And also the method is, to find a contribution, a local path contribution, you have to measure the whole structure. You can't just look at that particular path and just measure that. You can't do that with method. And also the frequency range of the test can be limited, because if you have long measurement times, you won't be able to cover the high frequencies. What we needed is a faster diagnostic method without sacrificing the accuracy. So what I thought is, okay, inverse measurement is very time expensive. So can we measure the block forces quite directly? So we can go back and look into the characterization of airborne excitation. Typically for airborne excitation, people have stipulated using block pressure as a source characteristic. And if you do some maths, you can find that the block pressure and the contact pressures are related through this expression, where this P rad is a radiated pressure from the partition back into your source volume. Okay, and for commonly used building partitions where the impedance of your structure is quite high than the impedance of the air, you find that generally this relationship holds valid, where the contact pressures are almost similar to your block pressures. And if that's true, then what you can do is you can just measure the contact pressures directly by just, with a microphone measuring all over the partition, and you can directly get your block pressures through your contact pressures. And to check the validity of this, you can do a pressure validation test. Instead of using block forces, you can use the contact pressures to perform the pressure validation. And so that approach sort of formed the DSC approach, which was the direct airborne source contribution analysis. Okay. So I did a simple test on first a dual glazing window, where I did this pressure validation using the source side pressures, and as you can see, pressure and predicted pressure up to like 1 kilohertz match very well. So that sort of tells like that measuring the block pressures directly as the contact pressures is very, very useful, because now you don't have to worry about any inversion process or anything. So the advantage is, obviously, you don't have to measure any structural FRFs, velocity sensors needed, and you can measure the contributions, the source contributions at least, directly, individually, and you can maybe automate the measurement as well. Okay, so some real life cases. So first, I had this double casement window, it's a commercial window, and wanted to check then if I can apply my methods on it, try to diagnose the contributions of the frames and the glazing separately. So what comes through the glazing, what comes through the frame. Okay. So to do that, what I, as usual, I first did some ISO 10140 sound isolation test. And then to measure the contributions, what I did is I applied the DASCA approach, where I just measured the contact pressures all over the partition at discrete locations, and measured the vibroacoustic transfer function. And first I did the pressure validation. So average sound pressure in the receiver room predicted by my approach, and the measured pressure looks very good up to 1 kilohertz. At low frequencies, I got some errors due to some errors in vibroacoustic FRF measurements. And once you have validated your method, then you can go and diagnose your contributions. So here, what I did is because of the construction of my window, the glazing and the frame are made of different materials, so their impedances are different, and also the glazing and frames are usually decoupled by resilient elements. So in that case, I assumed, okay, they almost act independently, or the or the sort of the flanking from one element to other is very less. So in that case, what I could do is I could just say, okay, I could measure just the source contributions, and there will be very good estimates of the path contributions. So these are the estimates of the contributions get using the SCA approach. Contribution is less, and that's what you actually would like, because you want to get the full benefit of the sound insulation offered by the glazing. So you would always want a contribution of your frames to be less. So it sort of shows the potential of the diagnostic test by quantifying contribution of different elements. I used it. Now here the actual glazing was very sort of heavy glazing material. So the mass per unit area was something like 50 to 60 kilograms per meter square. But the frame was really sort of light element. It was made from sort of like PVC type element, which is like plasticky element. So in that case, I did the same test to find out if the frame is sort of giving is transmitting more. So first did the same kind of validation first to look at how the pressure can be predicted to validate the method, and then I looked at the contributions of the frame and the glazing. So here you can see, of course, at low frequencies where you have a big sort of plate-like structure, you get of the glazing, you have the higher contribution from the glazing. But as you go up in the frequency, especially between 200 and 300, you get a crossover region where the contribution from the frame sort of exceeds the contribution of the glazing. So here, what you can see after like maybe like 250 hertz and so on, you are not exploiting the full benefit of the sound insulation offered by the glazing, because the more contribution is coming from the frame here, right? So if your frame is contributing more, you're not getting full benefit of the less sort of, or the sound insulation offered by the glazing. So in that case, it sort of tells you that you especially need a frame which will have at least the contribution less of that you can fully sort of explore the sound insulation offered by glazing, because that's your sort of heavy duty element in there, your glazing. So those were the two sort of case studies I did. And I then also wanted to look at some sound insulation formulation, if I could, have combined test where you can measure the sound insulation and also diagnostic information as well. So I looked at the literature and I found that, okay, some people have done contact pressure measurements to measure the SRI, and they found that the repeatability is higher than that of the repeatability SRI measurements. So I just thought, okay, pressures on the surface, can't we just use that for SRI? We have this improved repeatability. Okay, so if you want to measure the SRI using the contact pressures, the block pressures, you have this analytical equation for measuring the incident sound power, where the incident sound power is the auto spectrum of the block pressures and divided by this impedance term and the area term. And if you can measure the block pressures, you know the incident sound power. Transmitter sound power is not true, because you can measure that by a approach, standard approach, or other approaches. And then your SRI can be simply given by this relation if you know both these powers. And one thing that all these studies miss is they always assume that to use this kind of relation, they assume that the partition is blocked, but none of the studies really claim to have actually measured if the partition is blocked or not. To actually now check whether the partition is blocked, what you need to do is measure this re-radiated pressure from the partition. And if that is negligible, you can then tell, okay, then the contact pressures are almost similar to block pressures, or that the partition can be treated as a blocked, in the blocked condition. So I sort of formulated an approach to measure the radiated pressures. So similar to predicting in the receiver side, you can predict in the source side just by changing the vibroacoustic transfunction. You can just use the vibroacoustic transfunction towards the source side. So you can measure the radiated pressures using that relation, or using that relation, where the term S just represents the transfer function on the source side, not the receiver side. And as you can see, in blue, you have the contact pressures, and in red, you have the radiated pressures. And these are just sample results over 2 random positions on the window. And you can see the radiated pressure is always typically very, very low compared to the contact pressures. And if that is really that small, then the block pressures are almost equal to your contact pressures. That means you can treat the partition to be as block. That means you can use the relation, that relation then, for measuring the incident sound power. Okay, so I did that for both the window cases, just showing just one of the results here. And so I can measure the SRI now. So here in the top plot, I'm presenting the comparison between the measured SRI using the predicted using my block pressure relation. And you can see quite reasonable agreement up to my 2000 hertz, which was my sort of measurement range in which I was performing my measurement. And I also did the same thing for the single casement window. Again, a reasonable agreement for the ISO and the prediction SRI. So this sort of tells me that you can measure just one data set. You can measure just the block pressures and the vibroacoustics transfer functions, and you can find your diagnostic data, as well as you can predict the SRI. This could be useful in a case where, let's say, you can't satisfy the requirements of the ISO ISO standard, where you have to have the microphone positions like at certain distance from the rooms and from the walls and between microphones and so on. Where you can just use the approach using the block pressures, where you just measure close to the surface and you can predict the SRI. So in conclusion, I had 3 different methods which I developed, which is the 2 of them were inverse. One is the inverse method for finding source contributions, other is inverse method for path contributions, then a direct method for source contributions, and then formulated a sound insulation approach where you can actually utilize the in-situ measurement data for predicting your SRI. All right, so that's it for my presentation. Thank you for listening. Right.
So ISO is based on a diffuse field assumption.
Yeah.
You have to make the same assumption.
Yeah.
Your
Yeah. Only for SRI prediction, not for diagnostic.
Not for the diagnostic. To get the SRI,
yeah. That expression is formed from a diffuse field assumption. Yeah. So you can't escape that, but the advantage of that is you get improved. The uncertainty is less than your ISO. Both are based on diffuse field assumptions, but the uncertainty, that approach is very less. Yeah.
results in ISO one.
Yeah, it could be. Yeah, yeah, it could be. Yeah. Yeah. Yeah.
Which is true,
Mm.
but also same.
Mm.
So it's like same. So it's a
Yeah. 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 Only if they're not worried about the RW values, because
Yeah.
if they go with cheap, then their RW is going to go down and so on. Optimization, isn't it? Yeah. True. True. Anything?
Will the block pressures on partition change? Partition block pressure essentially block
Yeah, yeah.
the surface.
I haven't tried it out, but I suppose if, because the impedance of most partitions will be so higher than your impedance of air, I suspect they will be pretty much similar, but I haven't really looked into block pressures of different scenarios now.
Well, then I think rather than both to test in the same room.
Yeah, you just
block
measure it
pressure
once.
Would belong to the room, whatever.
Yeah.
Just to avoid to
Mm. Yeah. No, I just really asked Danny and just talked to the manufacturers myself, and they were like, okay. Yeah. That's it.
No. So,
Mm. Mm.
even if it's not
Yeah, it's like so they won't do it always, but if they're looking to improve or know more about their product, it's like a R&D investment for them. Suppose.
when you do contact
Hmm.
approach, measure the pressure of the reference.
Yeah, yeah. I use the voltage loudspeaker.
Oh.
Mm.
I mean, also because you're in a diffuse field, that phase reference.
It will help. I suppose there will be a cutoff frequency after which the phase will be random. I suppose. So I found that if you want to, so you can find the maximum frequency of prediction by it's dependent on the wavelength in your structure. So it's dependent on the bending wavelength. So it's like the maximum frequency of prediction is the where your grid size is less than or equal to lambda b by 2, so half of your bending wavelength. Yeah. Yeah, yeah. Yeah, yeah. So for the big window, I think I discretized it into like 140 or something little areas, and to get that prediction till 1 kilohertz. But another thing, what like scanning probe and some record position. So we have this microfilm thing which comes with the camera, and you scan it, and it also records the position because it's recording it constantly. So that would be, I think, very, very quicker because you do a scan, and it also records the position from the camera. It knows very quickly where you have measured that pressure. So that would be, I think, the next step, which would be very useful for reducing the time measurement. Yeah, very significantly. Yeah.